It's taking its time. Okay, so we can get started. We're going to continue our discussion of chapter 11. Let me back this up a bit. Okay, so the last thing we discussed, let me minimize this here. Put this up there. Okay, so the last thing we discussed were the allotropes of carbon, and I mentioned two allotropes. There are actually more, but these are the two main ones that often comes up in general chemistry discussion. You have the diamond and you have the graphite, and we talked about the arrangement of the atoms and so on. So the next thing we're going to talk about are crystal lattices, and we met this particular topic in passing when we were discussing ionic compounds, and we were talking about the fact that in ionic compounds, what you'll find if you look at things at the microscopic level, you'll find that there's a regular ordered arrangement of the ions, which continues throughout the growth structure of the compound. So you have what we call repeating units that can proceed in one direction, as shown here. All right, this is just a basically schematic representation of that. Or you can have it in multi-dimensional space, as you can see in this arrangement here. So this is what is oftentimes seen in certain solid compounds, usually ionic compounds, but even some covalent compounds, you'll see some of that as well. Now, the repeating unit that you'll find, we call it a unit cell, right, in the lattice, all right? So basically, that repeating unit that you'll see, you can identify, for example, in sodium chloride, we call that a unit cell. So just to give you a hypothetical example of a unit cell, if you... Hello? Folks, if you could please mute your mics.
You would already recognize them by the pictures and everything.
Oh, you see, a lot of people.
Okay, that looks like Lexi.
Well, he looks different compared to like that.
And
like,
that's what I was just about to tell you. A lot of people that run into me now say I look different.
Hello, Lexi.
My hair was cut low all the time, Lexi. I never grew out my facial hair. I always kept like a baby face. Okay, so with Matt, if he would have to,
I think you
can ask him if he ever heard of
yourself as the host.
Yeah, that's what I just discovered that. Thank you. Okay, so she's having fun over there. Anyway, what was I saying? So if you look at this hypothetical example here, let's say that this represents, a particular ionic compound where you have the ions occupying in a unit cell the four corners of a cube right here. Then that just basically continues this way, and this way. You see the same repeat pattern in terms of the arrangements of the ions, all right? Okay, so that's basically what we call a unit cell. Now, what you'll find is that in different compounds, different substances where you have crystal lattice, the unit cell will be of a different arrangement, all right? You can have what is known as a simple cubic cell, which is actually the simplest unit cell. And as the name suggests, basically it consists of 4 atoms or ions occupying the corners of a cube, all right? So we call that the simple cubic cell. And then we have something which is a bit more complex called the body-centered cubic cell, abbreviated BCC, where you have what we have here in the case of the simple cubic cell, but you have an additional atom occupying the center of that cube, all right? So that's called the BCC, or body-centered cubic cell, all right? Then we have another possibility, which is called the face-centered cubic cell, where again you have the atoms or ions occupying the edges of the corners of a cube, but on the face of each cube you have a separate atom, which is represented by the red spheres here. So the white spheres represent the atoms occupying the corners of a cube, and the red spheres represent the atoms occupying the center of the face of each face of the cube. As you all know, the cube has 6 sides, so therefore there'll be 6 atoms occupying the middle of each face, all right? So those are some possibilities in terms of how the ions or atoms, particles, whatever, would be arranged. Simple cubic, body-centered cubic, or face-centered cubic. So another terminology that I need to introduce to you is what we call the coordination number. And the coordination number is basically the number of nearest particles to a single particle in the crystal lattice. So for example, in the case of a simple cubic structure, the coordination number is 6, as you can see in this example here, where you have the central atom here, and or ion, and you have 1, 2, 3, 4, 5, 6 atoms or ions surrounding it. So we call that the simple cubic structure, and therefore the coordination number is 6. All right. So that's another term that you need to be aware of. Okay, so let's talk about packing in crystals. So open packing, as opposed to closed packing, is one that has, it's actually the less efficient way of packing atoms or ions in this sort of situation. So if you imagine this arrangement here, where they're basically a simple arrangement where they're just basically aligned like this and then like this, according to the rows or the groups going down. Basically, you'll notice that you have some relatively large spaces in between these particles, right? So that is called open packing. Now, a more efficient way of packing would be like this, all right? Where basically the spheres, for example, this one here is not directly on top of this one. It's actually in contact with these two spheres below it. And therefore, you'll notice that the space that is created here is larger compared to the space that is created here, all right? And so in this case here, the packing is more efficient, and basically it's close because you have less spacing between the particles, all right? Now, of course, as you can imagine, in nature, when we have these sort of particles packing, they tend to pack closely, especially given the relative sizes of the particles. So the next question is, how will the layers be formed? In other words, once you establish one layer that is packed efficiently, how can you efficiently pack the other particles on top of the first layer, all right? So if you start packing the particles of the second layer, what you'll find, and if you do so in the most efficient fashion, such that each particle here will be in contact with 3 of the lower particles in the bottom layer, then what you'll find is that there are 2 types of spaces that will allow for the third layer being packed. Now, these spaces are designated as the tetrahedral holes, which are indicated here and here, and the octahedral holes, which are indicated here and here. Now, you'll notice that the difference between the tetrahedral and the octahedral holes is that in the case of the tetrahedral holes that are created here and here, any particles that are placed here and here in the tetrahedral holes will be directly above a particle which is already in the bottom layer, all right? On the other hand, in the case of the octahedral holes, any particles that are placed on those holes here and here will be above spaces which would be created in the bottom layer, all right? So let's look at what happens in each case. So if you start placing particles in the tetrahedral holes, right, then you end up with what is called a hexagonal close packing arrangement, ACP for short, all right? So that's what you're doing here. You're putting particles in the third layer such that they are directly above a particle in the first layer, all right? So therefore, we call this arrangement ABAB, because the reason why we call it that is because what you'll find is that the first layer arrangement will be different from the second layer arrangement, but the third layer arrangement would be identical to the first layer arrangement. So we call this the ABABAB arrangement, which is the hexagonal close packing arrangement, all right? So as stated here, these produce 2-layer repeating units, AB, AB, and so on and so forth, all right? So that's a hexagonal close packing arrangement. And then when it comes to the other arrangement where you place the holes, you place the spheres or the atoms above the octahedral holes in layer B, then what you're going to end up with is these particles covering or being directly above spaces that were created in the first layer, right? So we call this a cubic close packing arrangement, and this is designated ABC, ABC, because the first layer is different from the second layer, which itself is different from the third layer. The third layer is different from the other 2. And then when you get to the fourth layer will be exactly the same as the first layer. So that's the reason why we call it the ABC arrangement. So as stated here, this arrangement will produce a 3-layer repeating unit. All right, so that's basically the cubic close packing arrangement as opposed to the hexagonal close packing arrangement. Is there any questions so far? Any questions? Any questions?
Are there even more? Are there any even more complex packing schemes? Like
I'm
this?
quite sure there are, but I'm quite sure they're also beyond the scope of this level of this course. I must admit that this particular topic is not exactly my expertise. This is in the realm of inorganic chemistry, and I'm an organic chemist kind of guy. So, you know, my knowledge of this particular topic is very surface. I know that it's very complex, based on especially talks I've been to where they talk about these things. Okay, so let me see what next. Oh, now I will say this. I've been scouring the internet trying to find diagrams which explains this or show this better than what we have here. So I came up, and my search is not exhaustive, admittedly, but I came up with a couple of diagrams. Now this one is showing you the actual arrangement in the HCP packing, where the repeat units will be AB, right? So this is the first layer, right, of the arrangement. Of course, they kind of show it spaced out so that it gives you a better picture. And then this would be the second layer, right, where the atoms here will be occupying the holes of the first layer. And then here, you have the third layer where these atoms are occupying the holes, which are just above or directly above the first layer, atom for atom, right? So this is above this is above this, and so on and so forth. So this shows you why we call it the hexagonal close packing, because if you look at this shape right here, it's in the shape of a hexagon, where you have 6 members here, and it's a hexagonal prism, all right? So that basically shows you why it's called the hexagonal close packing. Now, the other diagram I have here, to be perfectly honest, it's not very clear in terms of the ABC packing, showing it's a tetrahedral. So this is the one that I found. I'm going to see if I can find some others which are more clear. But this is trying to show you that it's a tetrahedral arrangement, which, to be perfectly honest, I can't really see the shape of the tetrahedron in this particular diagram. So I'm going to see if I can find another one which I can post in Canvas so that it will give you a better picture. But this is supposed to be the CCP packing of, you know, where it's an ABC repeat unit. I mean, I can identify the ABC because this is one layer here. This is and it's even not that clear in this case here, so I won't even try to show you. So I'm going to see if I can find a better diagram which shows you a clearer picture of the arrangement. All right. Okay. So sorry about that.
Yeah, you tried your best.
Which illustrates again why this is not my topic. And I never liked inorganic chemistry. I just had to do it in order to get through my degree requirements. Okay. So can we predict whether or not a structure will adopt the CCP or ACP arrangement? And people have done experiments on this, and what they have found is that there is a correlation between the ratio of the radius of the cation to the anion to whether or not the structure adopted would be the HCP or CCP arrangement. So, and these are all experimental results. So what they found was that if the ratio of the cation to the anion falls between these two numbers here, 0.225 to 0.414, then basically the arrangement would be the HCP arrangement, where the tetrahedral hole filling will occur, all right? On the other hand, if the ratio goes from 0.414 to 0.732, then basically this structure adopted would be the octahedral arrangement, I'm sorry, the CCP arrangement where the octahedral holes are filling. All right, so the first one would be the AB arrangement. The second one, and when I say AB, I mean AB, AB, AB continuing. In the case of the second one, the arrangement would be ABC, ABC in terms of the arrangement of the particles for each layer. And then if the ratio goes beyond 0.732, then the arrangement would be cubic, all right? Okay, so that's basically how you can make predictions as to whether or not the structure that would be adopted by a particular compound would fall into any one of these categories. So that means that you'd have to get some data and determine the ratios and then compare the ratios to the ranges that are given here to make those predictions, all right? So just to give you two examples of compounds, sodium chloride versus cesium chloride. So they both have in common the chloride ions, but the difference between them is that one has a sodium cation and the cesium cation is present in the other one. And what you're going to find is that because cesium is larger compared to the sodium ion. Now, I don't know what the actual numbers are, so to be perfectly honest, I cannot tell you which of these ratios or ranges they'll fall into to make the prediction. But what you'll find in this case is that in the case of the cesium chloride, you'll find that the cesium ion has 1, 2, 3, 4, 5, 6, actually 8 chloride ions surrounding it. And in the case of the sodium ion, it has 1, 2, 3, 4, 5, 6. So the coordination number of the sodium ion is 6. The coordination number of the chloride of the cesium ion in this structure would be 8, all right? And what you'll find is that in the case of the sodium chloride ion, it has a, if you look at the repeat unit, it's a body-centered, or I should say a face-centered crystal structure, right? So therefore, going back to this here, I think, hold on, let me just check something here. I think this, in the case of sodium chloride, is an FCC. No, I'm sorry. I think it's an HCP arrangement, whereas in the case of cesium chloride, it's a CCP arrangement. I'll have to look these up to explain or to know for sure, but I think that's the case. And the reason why that's the case is because the cesium to chloride ion ratio is larger compared to the sodium to chloride ion ratio. So if I had to guess, I would say the cesium to chloride ion ratio would be within this range here, whereas the sodium to chloride ion ratio is within that range. I'd have to actually get the numbers and do the calculations and see, all right? But I think that's basically the case when it comes to these two, all right? So those are just two examples of different structures adopting, different compounds adopting different structures based on the ratios of the anions to cations. Okay, one last thing I want to talk about here is how do we experimentally determine crystal structures? And we do that by an experimental process where diffraction is the underlying principle that we exploit. Now, I'm not going to go into the details of diffraction because that's mainly a physics thing. I remember when I was an undergrad, I minored in physics, and I remember we learned about this. But basically, what you see here is radiation that is used to basically shine on your crystal structure. And what happens is that they undergo what we call diffraction, and they're detected over here. And to cut a long story short, you see a diffraction pattern in a detector, and that gives you certain information, namely theta, and the wavelength you'd know based on the radiation that you use. And based on this equation, you can calculate D. Now, D is the distance between two closest particles in the structure, and half of that distance would be the radius of the particular atom or ion that's a part of the crystal structure. So that's basically the experimental procedure that you would follow in order to determine certain information, in particular the radius, the ionic radius of the ions involved, or molecules or atoms involved in crystal structures. All right. Okay. And with that said, believe it or not, that's the end of this chapter. And that's the end of this course. All right. So you might be wondering what's next.
What are we gonna?
Well,
eat?
what? Oh, you had a question? Sorry.
Yeah, I was just going to say, well, what now? We've got another month.
Yeah, exactly. We have about 4 weeks left. So basically what's going to happen is that I'm still going to be available during the regular class time, right? I'll be putting out the assignments for the remaining chapters. You have one more test. I'll make announcements about all of that. In fact, if I'm not mistaken, your third test was due or is due this week, but I'm going to put it off until maybe next week or the week after. I'll let you know. So that test is still coming up, third test. I'll be putting out assignments and let you know when they're due and all of that. And I will be available during class time. So if you have any questions or queries, feel free to come during class time. And in addition to the office hours, I'll also be available during the office hours. So if you have any questions, if you need help with anything, you can see me during class time and I'm there to help you with those problems. All right. So that's basically all I have for today. Are there any questions? Any questions?
I don't think so.
Okay, so let me take roll. Let me and I'm not going to be taking roll for the rest of the class since, of course, since it's optional for you to be here for the rest of the semester. So let me go here. Today is the 3rd. Okay, Arias Rios, I don't see her. Barber is here. Cannon is here. Chang is not here. Chavis, not here. Clark.
Here.
Yeah, Clark, you need to mute your mic if you're having private conversations. DeGraff, Franklin, not here. Han, not here. Panic, not here. Heron is here. Holland, not here. Oh, is here actually. Jorgensen, Rouse, Runnels, not here.
Yep. Nope.
Runnels is here. I'm sorry. Santiago is here. And Smith, okay. All right, so that's basically it. So if there are no questions, that's it for today. So like I said, I'll be here during the regular class time. So I may or may not see you next week if you decide not to turn up. So enjoy the rest of your day and I'll see you whenever I see you guys. Keep an eye out for the announcements because as I said before, I'll be giving you information about, quizzes, tests, and so on. Also, let me just say that one of my plans for today is to send back to you guys the graded tests that I just posted the grades for. So look out for that. I should have that done by end of business today. All right.
All right, cool.
I can't think of anything else by way of announcements. So that's basically it. So take care and enjoy the rest of your day.
You too. Take care.